Rust's ownership model can be quite daunting for newcomers, and that's okay. It helps solve a number of major memory vulnerabilities in older languages without relying on the overhead of a garbage collection system. It allows for fast and memory-safe programs, but it can be a little confusing at first. In the previous 2 episodes, we wrote a couple of basic embedded Rust applications to blink an LED and send strings out over the USB serial port. We're going to take a step back now to dive into the basic rules behind the ownership model. We won't need any hardware for this episode, as it will just be quick snippets of code that can run on your computer. Before we start, we should talk about the different places in memory where your data can be stored. In many applications, you will find RAM for your program mapped something like this. We'll ignore the program instructions or .text data for now, as we'll assume that's in a separate section of flash memory. At the lower RAM addresses, you'll find a place for initialized static and global variables, often abbreviated as .data. Then, you'll find an area for uninitialized static and global variables, which is usually labeled .bss. In many embedded systems, you'll find an area for data that persists between reboots. This usually gets a label like .uninit or .persistent. After that, you'll find the heap. This is a general pool of memory for dynamic allocation. If you've worked in C, when you call something like malloc, it will reserve a section of heap for you to use in your program. Usually, the compiler does not know how much memory needs to be allocated at compile time, so it just lets the heap dynamically grow and shrink as needed as the program runs. In most cases, including our Raspberry Pi Pico 2, the heap will grow towards higher RAM addresses. In the last section of RAM, toward the highest addresses, you'll find the stack. This is a last-in, first-out data structure for allocating data for local variables, function parameters, and return addresses. Data here usually gets automatically cleaned up as variables go out of scope. While the maximum stack size can be determined at program startup, the used portion will grow towards lower RAM addresses as needed. If heap and stack meet, bad things happen. This is known as virtual address space exhaustion, or simply an address space collision in colloquial terms. You might simply not be able to allocate memory, or data might get corrupted, or your program might crash. Some embedded hardware or software frameworks add protections and guards to help prevent such collisions. We won't get into them in this series, as nothing we're doing uses that much memory. Another way around this is to avoid using the heap altogether, which is a common practice in embedded systems. Because you can determine the maximum stack size at initialization, you can easily test to ensure that your program won't run out of memory. I bring this up because most of the ownership examples in the Rust book rely on heap examples. While you can enable the heap in many embedded systems, we'll actually be creating mostly demos without the heap and without the standard library, which gives us types like strings and vectors. Let's take a look at the 3 main ownership rules in Rust. If you worked through chapter 4 of the Rust book, you'll probably notice that they used strings for all of their examples, which is great except for the problem that most of the time these string types exist in heap, and string is part of the standard library, which we won't be using for most of our embedded examples. So let's find a different way to do this that still demonstrates all of these ownership examples. In the Docker container, I'm going to go into Workspace Apps. I'm going to create a new project with cargo new. Let's call it Ownership Examples. We'll say this is a binary or executable, and we'll say version control system is set to none. With that created, let's open up our ownership examples, go into source, open up main. Let's delete this main function so we can start creating our own. Instead of strings, we're going to use this custom sensor reading struct. It's just some dummy values put in a struct. We're going to have one value be named value, and that's going to be of type unsigned 16-bit integer, and another that is a timestamp ms for milliseconds, and that is an unsigned 32-bit integer. This might be a wrapper for some sort of sensor reading you might get. By using primitives inside of a struct, we can guarantee that this information is stored in the stack, but we can still use references to it in order to demonstrate the ownership and borrowing rules. The first rule, and this is right out of the Rust book, says that each value in Rust has an owner. In this case, we'll let reading, our variable, be the owner of this new sensor reading struct with this data that's been filled out. If you haven't played with it yet, note that this uses the values or value and timestamps display trait if that's available. So if that's been implemented, which it should be for most primitives in Rust, we can display them using these curly braces. Let's save this. We'll go into our ownership examples. We'll say cargo run, that should build it, and sure enough, that prints it out. So this demonstrates that reading has ownership. Okay, that's not very useful, so let's see how the rules expand to flesh out the whole ownership model. The second rule states that there can only be one owner at a time. So let's create our immutable reading variable, and we'll set it to be the owner of our sensor reading, which has the data value 2 and timestamp of 100. Now let's create a new variable. We'll call this one new owner, and we're going to say equals reading. In Rust, this is considered a direct transfer of ownership, or it's also called a move. Now, at this point, so at the end of this line, new owner is the owner of that sensor reading we created. If you try to do this to a primitive, note that Rust automatically performs a copy of this primitive. So reading would be value 3, and new owner would also be value 3 because that value was copied to new owner, not transferred. It assumes you want to copy things like primitives because there's not a lot of data in them. Let's go back to this struct, and then by default, this is a move of ownership because it's a struct. You'll see this for things like strings and vectors in the standard library as well. This is an actual move. So what happens if we try to print the values inside of the sensor reading struct after we've moved that struct to a different owner? Save your file, say cargo run, and sure enough, you get a compile time error. This says borrow of moved value reading. So the value moved here on this line that we showed earlier, and you can no longer use it because essentially this doesn't work anymore. This is no longer the owner of sensor reading. If you were to implement clone, the clone function for this struct, and give it a specification on how to actually copy the values within, this might actually work and you could call clone here. But since we did not do that, this fails. I'm going to make a note about where that's failing. And then, as can be expected, we can use our new owner and print out the values within. So let's save this. Let's run it again. Sure enough, it builds and prints out the values without a problem. So I mentioned that you could implement clone for this. You can also do deep copies of things if it's been implemented, and arrays actually, by default, implement the copy trait, assuming each of the elements also implement the copy trait. Let's see an example of that. We'll do a little Fibonacci sequence here, and then we will do something that looks like our move earlier, but because arrays by default implement copy, assuming all the individual elements implement copy, Rust thinks you're trying to copy the array here. Keep this in mind if you have large arrays, because this might be a deep copy of the array, which could consume a lot of clock cycles. So keep that in mind. So as expected, we can actually print out or use the values both in my array and my copy. This colon question mark inside these curly braces, this is the debug format specifier. This uses the debug trait that's implemented by default on things like arrays in order to print them out. Let's save this. We'll say cargo run. We get this warning saying we're not using sensor reading. That's okay. But otherwise, it prints out both arrays because it has been deep copied in this line here. All right, let's get rid of this. The third rule is that when the owner goes out of scope, the value will be dropped. Let's make a note about what scope actually means here. Scope is the region of code where a variable is valid and can be accessed or seen. This is usually between curly braces in things like functions or loops. But note that we can just put curly braces in the middle of a function right here, and this creates a new scope for us. So let's see what happens when we try to run this where we initialize this reading variable inside of a new scope, exit that scope, and then try to print it. So let's save, and we'll try to run it. Sure enough, we get some errors. It cannot find reading in this scope. So let's make a note about this. According to rule 3, reading went out of scope right here. In fact, the compiler sees that it's no longer used within this scope and drops it right at this point. That means freeing up the memory consumed by sensor reading. Instead of a garbage collection system used in other languages like Python and JavaScript that come through and look for pieces of memory that are no longer referenced, Rust attempts to do this essentially all in compile time. There is a little bit of runtime overhead to actually do the free on the back end, but the compiler sees that reading is no longer used in this scope and immediately frees up the memory taken up by sensor reading. So the value is dropped, the reading variable is no longer valid, which means we cannot use it here any longer. This helps prevent things like use after free, double pointers, and memory leaks. These are common memory errors you'll find in things like C and C++. So we know this line doesn't work anymore. And to demonstrate this even further, let's create a new function. When we pass in a value like this to a function, we say that ownership of that value is consumed by the function. It's actually moved or transferred in, as we saw in rule number 2. So we can pass in reading, but then this function now owns reading. This will work. It will print out right here. But as we saw with the scope earlier, because this is a new scope within the function, reading will go out of scope right at this point, so the value is actually dropped, and the memory is freed. Let's try this. We will pass in reading to this print reading function. Ownership is passed to the function, and this should print out. Let's save it. Let's go ahead and run. Great, it worked. We printed out 3 and 100 from within this function. So what do you think will happen right here? As I mentioned, we passed in reading, and we passed ownership to this function. Reading goes out of scope, and that's it. We no longer have reading here. So this should fail. We should not be able to use reading any longer because it went out of scope. Let's save this. We will run it. Sure enough, here is that error. This might be a little cryptic at first, where it says borrow of moved value reading. That's because println is actually using some references, which we'll explore next. So we're trying to borrow the values here, but it's already been moved. And in fact, scope dropped here and the value dropped. So that's the error you will see if you try to use something that's already been moved and consumed and you no longer have ownership of it. So we have this error right now. Okay, how do we fix this? One way to do this is we can create a new function. So I'm going to comment that out. And under here, let's recreate this function. Great, same signature so far. We have the same function name. We are passing in reading. It is of type sensor reading. But guess what? What if we went ahead and returned ownership of that exact value? So that is giving the return type of sensor reading. We have the exact same internals of the function previously, but we're going to actually return that value. Note that this is the verbose way to say return a value from a function. We're going to say return and the name of that variable. However, you'll find that many Rust programmers, or Rustaceans, won't use this verbose syntax. You'll just see something like this, which means return reading. So we don't use the return keyword, and we don't use a semicolon here. And this is just shorthand for saying return this value. You'll see this a lot in Rust. So if you don't see a semicolon, it means that the value is being returned up to the caller. Okay, so the last thing we need to do is we called our function. Let's save this. But where we called the function, we expect it to return reading from it. So we gave ownership to the function returned ownership, and we put that ownership back in the same variable. Now we should be able to use it again. So we should see the values printed out twice. We saved that. Let's say cargo run. And you'll notice something interesting here where it says cannot assign twice to the immutable variable reading. Aha! Because we initially, by default, set this to immutable, and we're trying to overwrite that value, even if it's the same value. To fix this, we just say, let this variable be mutable. And in fact, many of the compiler errors will give you some really good hints here to say, hey, why don't you add mutable, or the mute keyword, when you define the variable. Great, let's do that. We'll save, and we'll run again. There we go, it's printed twice. So we've successfully demonstrated how we can pass ownership around and noted that values are dropped and memory is freed up once the owner goes out of scope. Raw pointers in Rust, like pointers in C, store the memory address of another value. References, on the other hand, are like a safety wrapper around raw pointers. They come with additional compile time checks to prevent most memory issues, like use after free and double freeze that can crash programs or introduce vulnerabilities in applications written in other languages, like C and C++. They do not have any additional runtime overhead and operate just like pointers under the hood. The Rust compiler, including the borrow checker, ensures that you do not use references in an unsafe manner. In the vast majority of cases, you will store values directly in variables or use references. You will only ever need to use raw pointers for very low-level code, like talking to registers directly, creating custom data structures, or interfacing with assembly. The Rust book uses strings to demonstrate pointers and references. In this demo, S1 is a string struct, which contains a pointer to data on the heap. Len for the length of the current string, and capacity for the number of elements that can fit in the currently allocated space. The example then creates a reference to S1 in the calculate length function. The parameter S is the reference. It's a safe pointer to the string struct. Both S and S1 live on the stack, but the actual string data lives in the heap. In our examples, we'll avoid using the heap so you can see how references work on data just in the stack. We've been working with the custom struct sensor reading that has the two unsigned integer values, value and timestamp ms. Let's say we create such a struct stored in a variable named reading. Unlike the standard library string type, the data for this struct lives on the stack. Now, let's say we create a reference named myref that points to reading. Both myref and reading live on the stack. This allows us to demonstrate references and borrowing rules without needing to use the heap. Back in our code, let's go ahead and delete our third example and move on with the fourth. The fourth rule states that you can have either one mutable reference or any number of immutable references. So we'll start by creating another dummy sensor reading here, and we'll assign it to reading. So reading has ownership. We're going to create a new function. And in this function, we're going to have our parameter be reading, but it's going to be a reference to a sensor reading value. In Rust, this is referred to as borrowing, where we borrow a value. You can think of it as like looking at a value through a window, but you don't have ownership of it. In this case, it's not mutable. We can't change it. So you can look at it. In things like C and C++, this is also known as passing by reference. Let's go ahead and print the values just like we did last time. As we can see, we don't actually need to return ownership when we call this function. So we can pass reading in by reference. That will print out the values, and we still retain ownership of reading. Let's save that, give this a shot. Sure enough, it prints twice because we never gave up ownership and the value never got dropped. With references like this, we can prevent things like data races where you have multiple threads trying to change the same data, modifying a collection while iterating over it, and reading stale data while something else is writing to it. These are common errors you'll find in things like C and C++ that don't enforce these types of ownership rules. Now let's see this fourth rule in action. We're going to remove this line. So the first part says that we can have any number of immutable references. So let's create immutable references 1, 2, and 3, and assign them all as references to the reading struct. If you're used to working in things like C and C++, you're probably used to having to explicitly dereference things like pointers. In Rust, you can explicitly dereference things. So in this case, we are going to use the star or asterisk and say dereference immutable reference 1 to get the value or to actually get the real struct, and then we're going to get the timestamp value within that struct. This works. However, Rust can also figure out, the compiler can figure out what you're trying to do and say, oh, you want the timestamp value from within the struct, go ahead and automatically dereference so you don't have to explicitly dereference. You won't see many explicit dereferences throughout Rust, but know that that is what's going on in the back end, is the compiler figures out that you're trying to dereference and just does it for you. Let's save this. We'll run again. Sure enough, it prints it from the function here, and then it prints timestamp from each of the references. So we can see that we are able to use multiple immutable references. Another way to think about it is you can have multiple windows looking out to the same object. Imagine it as a ball on a grassy hill, and you can look out of a house, out of any number of windows, and see that ball to get the information about it. Now here's where the rule comes into play. We can only have one mutable reference at a time. Think of it like reaching through the window in order to pick up the ball. The syntax for this is to use the ampersand for reference and then say mute right after it. So this creates a mutable reference, and then we give it the original value, or the thing that has ownership. And we assign that to a variable. So now mute ref1 is a mutable reference to reading. We can use this mutable reference to change the values in the actual struct. I'm going to print out the timestamp value from the original struct, not the mutable reference here. So pay attention to that. We are changing values in the actual struct. Let's save that. We'll run again. Aha, we can't borrow this as mutable. Why is that? Because the thing we're trying to change needs to be mutable. Okay, so that's helpful here. So we're going to go up to let reading, and we're going to change this to mutable. So now the thing itself is changeable, is mutable, and we have a mutable reference. So now we can actually change values within this struct. Make sure to save that. Let's run again. Sure enough, it prints the 3 immutable references, and it prints this one here. As I mentioned earlier, the compiler actually sees that we no longer use the immutable references after this, and so they are considered out of scope at this point and are dropped. So we're not really testing our fourth rule here. Let's go ahead, just for fun, print out one of the immutable references to demonstrate it's still in scope. Oh, wait, what's going on here? We cannot borrow reading as mutable because it's also borrowed as immutable. As I mentioned, from rule 4, you can have one mutable reference. You cannot have immutable references at the same time. You have a mutable reference in the same scope. So even if I put this up here, in between these two, can you guess what's going to happen here? All right, let's try again. Sure enough, the same problem occurs. Because mutable reference is in scope at this point, it doesn't go out of scope until here. And even if we tried to borrow a new immutable reference, same thing happens. So these 3 actually go out of scope here. And we've seen this before. This is an example of what's called non-lexical lifetimes. Strictly speaking, you would expect them to be in scope until the end of the curly brace here, but the compiler sees that they're no longer used. You don't use immutable reference 3 anymore in here, so it's actually considered out of scope the last time it's used, or when it encounters the end of a scope block. So that's non-lexical lifetimes. And we just saw that we cannot have immutable references in scope at the same time we have a mutable reference in scope. So let's comment these out. I'm going to make a note here. I'm going to grab this error so you can see what's going on here. Yeah, from here. Okay, what if we tried to get a mutable reference? Let's save this. Aha, this also doesn't work because of rule 4, one mutable reference. That's it. Once you have that out and in scope, you cannot have a second mutable reference and you can't have any other immutable references. So mutable references really are exclusive. I'm going to go ahead and comment this out. I'm going to make a note here so it helps you remember when you go back and look at this about what's going on when you have a mutable reference in scope and you try to borrow either another mutable reference or get an immutable reference. So now that mutref1 goes out of scope at the end of this, remember that non-lexical lifetimes that happens here. So mutable reference 1 goes out of scope, but reading is not dropped. Reading still has ownership of that struct, which means we can then borrow either mutable or immutable again. So let's try borrowing a mutable reference, changing something, and then we should be able to print out the value from that original struct that we changed with that mutable reference. So save that. Let's cargo run. And sure enough, the whole thing works. And we can see where we changed it the first time with the mutable reference to 1,000 and changed it again to 2,000. All right, let's move on to rule number 5. This rule states that references must always be valid. Let's create a very simple function here. This is just going to return a reference to a sensor reading. In here, we will create some initial sensor reading, let's say value 5 timestamp 100, and we're going to return a reference to that, hence the ampersand. All right, in our main, let's go ahead and call that function, and we will assign the output of that to, say, reading. Can you guess what's going to happen now when we try to run this? All right, let's save it. Let's run it. Oh, it failed. Why do you think that failed? Well, we tried to create a new value here in some reading, and then we create a reference to it and return it from that function. But remember the rules that we've already described about things going out of scope. In this case, the compiler does not look into the function when it's going through main and see that it should keep some reading alive. Because some reading goes out of scope at the end of return reading, that value is dropped, the memory is freed up, and this reference is no longer valid. This helps prevent errors that you might come across in other languages, like dangling pointers, use after free, stack frame corruption, and accessing invalid iterators after the underlying data has changed. That's like doing things like a for loop where then you change the iterator number. That can lead to a lot of problems. So just remember, some reading goes out of scope at the end of this function because we're not returning it, we're not returning ownership, and so this reference is no longer valid. The compiler catches that and throws an error. The error you'll see a lot of times is cannot return reference to a local variable. You've defined a local variable, you create some reference to it. Once the function goes out of scope, that local variable goes out of scope, that reference is no longer valid. So we can go ahead and get rid of this, and let's see the fix here. As we saw previously, you can return ownership, and in fact, you can create a new struct or value or chunk of memory inside of a function, and then you can return ownership of that. This is completely valid. You might get a compiler warning here saying that you should just return sensor reading by itself without first assigning it to a variable like we're doing. So it's generally more idiomatic to do that rather than assigning it to some intermediate variable, but I'm going to keep that assignment just so you can compare it to the wrong function above it that didn't compile. Let's save it. We'll run. Sure enough, it builds. We didn't get that warning, and we have 5 and 100 because we now have reading obtaining ownership from the function. In fact, you will see this used quite a bit in structs and methods and a lot of APIs where you will have a new function that returns ownership of the underlying struct for you. The basic rule to keep in mind here, and another way to remember Rule 5, is that a reference to data cannot outlive the data itself. So once this is dropped, this is no longer valid, but we can return ownership of the underlying struct or value. Okay, let's go to rule number 6. This states that if you move out part of a value, you cannot use the whole value anymore. This helps prevent errors like use after move, double freeze, inconsistent value states, and memory layout corruption issues. Let's see what this looks like in action. Let's create a tuple here that is two sensor readings. They both have the same value, and let's just have the timestamps be 1 apart. Now let's partially move ownership. We'll create a new variable called firstReading, and we will assign to it mytuple.0. Note that tuples don't use the brackets to index into them like you would find for arrays. It uses this dot notation. So .0 refers to the first element in that tuple. So we can print the new owner that we've called firstReading that owns this first element in the tuple. So we'll get value and timestamp and print it to the console. And we can also move and borrow the other parts. So we have mytuple.1. We will print the value there and print the timestamp of that second element as well. Let's save that. Let's run this. It looks like I have a syntax error. Aha, forgot a semicolon. Let's save that, run it again. Sure enough, we printed out both. So firstReading now has ownership, or partial ownership, of the value here. Now let's try to print out the value in that first element of the tuple. Remember that firstReading now has ownership of this element in the tuple. So let's save, run it. Sure enough, we get an error here. This says borrow of moved value. So remember, we actually moved ownership in this line right here. And so now we can't borrow it because mytuple.0 no longer has ownership. firstReading does. So let's make a note that we can't use the value like this anymore. And we're going to go ahead and comment that out. All right, what happens if we try to move ownership of the entire tuple into new owner, and we'll try to print out the second element in here, and we will try to print out value in that second element. Remember, we've only taken ownership of this first element in this line, and now we're trying to take ownership of the whole thing and print out that second element. What do you think will happen? Let's save, let's run. Sure enough, there's an error. That's because of this second part of this sixth rule. You cannot use the whole value anymore. And that's because we've partially moved the original value, mytuple. We can't move ownership or use the whole value as it stands any longer. So let's make a note there. And we will go ahead and comment this out. So that is a demonstration of the sixth rule. Let's move on to the seventh and final rule. Here, we see that slices are references to the whole value and follow the same borrowing rules as we outlined earlier. Let's start this demonstration off by creating an array, not a tuple this time, of sensor readings. We'll have 3 sensor readings. Each of them has value 7, and the timestamps increment by 1. A slice is a section of the array. We do this by creating a reference to the array, so ampersand myArray, and then we use these brackets and the ... notation to show between the first and second indexes. So we want all of the elements between those indexes. Note that it is inclusive for that first index and exclusive for that second index. So here we are essentially just borrowing the first element. What's important to note is that even though we're just getting a reference to particular elements in the array, we're actually borrowing the entire array as immutable in this case. Let's just go ahead and print out the values in slice 1. So note that slices act like arrays, so we can index into them. So we will get that first indexed value. In this case, there's only one value in there because we just wanted that first element anyway. And we will print out value and timestamp. Let's go ahead and run this. Sure enough, we see 7 and 100. Let's try to create a mutable slice. In this case, we'll get myArray, and then we'll do the other 2 elements. So we'll say 1 ... 3. So even though this first element belongs to slice 1, and these second elements belong to slice 2, remember that slice 1 now essentially has a borrow of the entire array, at least an immutable borrow of the array. Let's go ahead and try to print out the elements in slice 2. So there should only be 2 elements. So we should be able to print this one and this one. Let's save this. We'll try to run it. Sure enough, we get an error. You'll see here we cannot borrow my array again because it's already been borrowed here. The whole of it, even though we only tried to borrow this part of it. That's just how the rule is. It's treated as the entire array when you try to create a slice, and you get that reference. And it follows the same borrowing rules we saw earlier, where you can only have one mutable reference at a time. So with our immutable reference still in scope, we cannot create a mutable reference. That violates the rules. But if you remember what the rules say, we can have any number of immutable references to the same thing. So we can just create an immutable reference here and still be able to print out the values. Let's go ahead, save, and run this. Sure enough, we print out all the values using slice 1 and slice 2. You will see slices used a lot for referencing things like contiguous sections of elements and arrays like we've done here. Also in collection types found in the standard library like strings and vectors, and other heap allocated data managed by smart pointers like the box. We won't run into those a lot in embedded code though. You can also find them used on some third-party crates like the heap list crate, so you will see slices used quite a bit even in embedded code. While this demonstrates that slices follow the same borrowing rules, I want to show you a useful method you could use to actually get mutable references to slices. And this is implemented for many of the primitives available in Rust. Let's delete our main function up to where we create my array, because we're still going to use that as an example. The function is called split at mute. This divides a mutable slice into two at a given index. And we need to make this actually mutable so we can change things. We'll go ahead and change the timestamps in those values by accessing through the mutable references. Note that the index given to split at mute is exclusive for the first slice. So when we give it 1, that means just return the element at index 0, which is this first one here, to slice 1. And notice we give it a tuple. And then 1 and then to the end of the array, so that is element 1, and whatever else is in that array go into slice 2. As we saw before, if we no longer use slice 1 and slice 2, they go out of scope right here. Now let's print out the values from the original array. So we changed values by creating mutable slices or mutable references. We change those values. Those references go out of scope, but the original values in my array should keep whatever we change them to and print out those new values. So even though we set them to something in the hundreds, they should actually print out something in the thousands. Let's save and run this. Sure enough, you can see how those original values in my array were changed by these mutable references. Now, what happens if we want to change something else using my array directly? Let's go after we've created the split. Let's try to access my array directly. What do you think will happen? We get an error. And you'll see probably one or both of these errors where you cannot use my array because it was mutably borrowed. So it was borrowed here. And once you've borrowed something, you cannot use the value directly. This is to prevent things like data race conditions where you're trying to write to the same thing twice, say from different threads. Or you might see something like this, cannot assign to this because it is already borrowed. So let's make a note of that error here. We will comment that out. But remember, slice 1 and slice 2 have gone out of scope here, which means that once they go out of scope, we are free to change that array directly. Now, let's save and run again. Sure enough, we changed the timestamp in that first element, and the other two remained what they were changed to through the mutable references here. All of the examples I have just shown you can be found in the GitHub repository if you'd like to review them. They're all together in one file. I hope this gives you a good starting point for understanding how the ownership model works in Rust and how to work with references. Let's review the ownership and borrowing rules in Rust. 1. Each value in Rust has an owner. 2. There can only be one owner at a time. 3. When the owner goes out of scope, the value will be dropped. 4. You can have either one mutable reference or any number of immutable references. 5. References must always be valid. 6. If you move out part of a value, you cannot use the whole value anymore. And finally, 7. Slices are references to the whole value and follow the same borrowing rules. While there are some esoteric edge cases that we did not cover, these 7 rules should give you the fundamentals of working with owned values and references in Rust. Memorize them if you need to, or you can use the code samples in the repository if you need a reference guide. You'll see these rules in action as we continue building out more embedded Rust demos. At this point, you can continue reading the Rust book up through chapter 9. You've already seen packages and crates. In the next few episodes, we'll be using structs, enums, and error types, and I recommend being familiar with those concepts. If you want some hands-on practice, I recommend tackling the structs, enums, modules, and error handling exercises in Rustlings. Feel free to also do vectors, strings, and hash maps. Just know that we won't see much of those in the embedded world, as they rely on Heap and the standard library. In the next episode, we'll get back to embedded code as we see how to use the RP2350 I2C library to read data from a temperature sensor. Happy hacking!